Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Can I start then? Okay, great. Thanks. It's nice to be here. So I'll be talking about a linear algebraic way to do list error correction and its connection to a fairly nice concept in algebraic pseudo-randomness called subspace-evasive sets. And this is a line of work which has been going on for a couple of years with a few papers, but the specific technical aspects I'll focus on is based on works with chopping zinc. Okay, so I'll start without assuming any background about codes, but I think most of you have seen some of it. So just a quick introduction. So a code, okay, so this is not so great. So a code will just be a subset of sigma to the n. So this is some finite alphabet. And typically you might think of sigma as 0, 1, so coding over bits, but actually for this talk sigma will be a large finite field or a large alphabet in general. So that's all a code is. So it's just some collection out of all the n bit or n symbol strings in sigma to the n, you take some collection. And then the rate of the code is the number. When you send a code word, you're communicating log c bits, logs are to the base 2, let's say, but you're actually sending n log sigma bits. So that's the rate at which you're communicating, because to send log c bits, you're going to be sending these many bits. Perhaps a more intuitive way to think of that is that you can think of a code as given by an encoding map. And typically this is the way I will present codes in this talk, is an encoding map E, which let's say maps sigma to the k to sigma to the n. So it takes k symbols, it's a message m, k symbols. This is in sigma to the k, and it stretches it to a code word C. So it's an injective map, and this code word will sit in sigma to the n. So what a code does is it adds redundancy to a message to elongate it to a longer string which is redundant. And why you do that is that maybe some symbol in this code word when you send it gets dropped, so you would like to recover the message based on that. And one simple way you can think of a code word as simply is the message followed by some check bits or check symbols. So maybe a simple example would be a sequence of bits, and then you could add a parity check, or you could have more parity checks. And the codes I will give won't be in this form, but it's really easy to move it between these forms. So for us, we will just take a message m and map it to a longer string. And why you do this is to correct errors. And in this talk we will be, and there are various models of errors. For example, for bits you could say each bit is flipped independently with some probability, each bit is erased with some probability, and so on. So we will be dealing with large alphabet codes. So sigma is a large, think of it as a packet. Okay, so code word consists of several packets, and we will be working with worst case errors. So what this will be parameterized by a single real number tau, which is between 0 and 1. And what this means is that when you send n symbols, the channel can corrupt some tau n up to tau n fraction of them. So I'll write that. So channel can corrupt up to tau n symbols are adversarial. So the channel can choose any subset of symbols comprising at most a tau fraction of the n symbols, and it can change it to whatever it wants. And then from that string, you would like to recover the code word. And it's good to have a geometric view. So code words are a very sparse set of all possible sequences, right? So because it's a subset of sigma to the n, and when you send a code word, the channel is basically going to distort it in some Hamming metric. So this is the code word, and this will be the received word, and delta CR is at most tau n, and this is the Hamming distance. Okay, so that's our model. So now, so typically there are two algorithmic problems with the code. One is to do the encoding, where given a message, you would like to compute the corresponding code word, and that's usually how you specify a code. In fact, you say, when I give you a nice code, I'm going to tell you how to do that encoding. The other converse problem is going to be harder, where you get, if you got a code word, then inverting this map will be easy, That's not going to be difficult, but when you take a code word and distort it, and now you would like to find out, now the algorithmic problem is going to be, so you have these code words, now given this received word, you would like to look in a radius of tau n and see whether there is a code word, and if so, output it. Okay, that's the decoding problem. So just formally, so decoding is given, so you fix the code. So the code is designed, picked by the designer. You pick some nice code where these points have some nice structure, which will allow you to solve this problem. So given some received word y in sigma to the n, compute c in the code such that delta yc is at most tau n. And this is called correcting tau fraction of errors, of worst case errors. Right, because this is exactly the problem. You're going to get some arbitrary point y, so I call that r here, the same thing as y, and you would like to find a code word within that ball. Okay, that's the decoding problem. And of course, there are two simple approaches to do this, which is to just go over all code words and see which one lies in the ball. That's going to take too much time. Or you could look at all points inside this vicinity of y. That's also going to take too much time. So the idea is, so there are exponentially many points, so you would like to solve these in poly n time. So that's the game. And really the trade-off which we like to, the trade-off which we are after, so this is all just context to what we are going to be doing. There are two key parameters here. One is rate, and that tells you how efficient your code is. So as you pack more and more points in sigma to the n, your code is more efficient. There is less redundancy. So that means high rate. But then it's intuitively clear that these points are going to come close to each other, so you won't be able to correct more errors. So really what we are interested in is this fundamental trade-off between tau versus r.
This is not list decoding, is it?
Okay, so I'm deliberately being sloppy here, so I'll come to that in a second. Yeah. So we will see that for the kinds of tau we need to correct, we won't be able to compute C unambiguously always, so we will have to make a relaxation. Okay, so I'll come to that in a second. So first I want to place some simplistic limit on tau as a function of r. And that comes from the following thing. So if you think of this message, so let me take this view. It's the same thing here, but your code consists of the message followed by some check symbols, right? And this is Rn symbols, because that's what the rate is. And this is 1 minus r times n check symbols, right? So now if the channel is allowed, if tau becomes 1 minus r, then the channel can simply, or if tau exceeds, I just want to say that if tau is more than 1 minus r, then correction is sort of hopeless. Because then what you can do is that the adversary can basically destroy all these check symbols and a little bit more here. And so then you have no idea what m would have been up to, or you would, there will be too much ambiguity in what m is. I mean, this is simply just an information theoretic fact. Because you have to recover Rn symbols, you have to get at least Rn symbols correctly. Otherwise, how are you going to recover this? And this is true even for a very simple model which just erases symbols and tells you which symbols it's going to erase. Even for that model, you cannot correct. You cannot produce more information than what your code word gives you. That's all this is. So clearly, tau must be less than or equal to 1 minus r. So that's a very very simple limit. But it turns out, so this is the point about list decoding which I want to get to. So it turns out if a code has, if C has rate r, implies there must exist two code words C1 not equal C2 such that their distance is at most 1 minus r times n. Okay, this is a very simple pigeonholing argument. Okay, if you have sigma to the Rn code words in the first Rn position, some two must be equal, and so their distance will be at most this. And what this means is that if I have C1 here and C2 here and their distance is at most that, I could get a received word which is exactly in the middle. This is my y. And now, so it could be the case that both of these are at most 1 minus r by 2 times n. Right? The midpoint will have this property. And this says that the moment tau is, which implies tau greater than 1 minus r by 2, so therefore, tau greater implies cannot always recover a unique C to this problem. Okay, so you cannot always give a unique answer. So the way we are going to relax this thing is that our goal is still going to be given a point y. We would still like to find a code word within this distance, but it could be the case that we are unlucky and there are more than one code word. In that case, we will just ask the decoder to output all of them. Okay, and the rationale is that that won't typically happen. So if noise actually happens in some random way or something, so you won't see that scenario. And even if you see that scenario, it's not so bad. Instead of all possibilities, you are saying it's one of these 5 code words. Let's say that's much better than simply giving up. Okay, so now that comes the list decoding problem for a code C. Given y in sigma to the n, find a list, or it's really a set, but it's somehow historically called list decoding. You could perhaps sort it by the distance or something like that. So maybe not everything in the list is equal. So maybe list is fine. List of all C in C such that the distance is at most tau times n. Okay, so this is the list decoding problem for error correction radius at most tau. Okay, great. But now a nice thing happens. The nice thing is, so we had this very trivial limit that you cannot go beyond 1 minus r. I mean, that was a really simple limit, but now, and somehow if you wanted to always get a unique answer, you were quite far away from that. Right? So typically in coding theory, people like plots. So one thing you can plot is the rate versus the error correction radius, and this 1 minus r is this line. Okay. So this is the trivial limit, and this unique decoding limit, where if you want a unique answer, is half this. Okay, so this is 1 minus r by 2, this is 1 minus r. So there's a big gap. So you cannot go beyond this. But now in the model of list decoding, it turns out it allows you to go all the way up to this. So this is the tau is 1 minus r ratio. Okay, this is 1, this is 1. Okay, and that's the theorem. So a surprising fact is that list decoding allows one to approach tau is 1 minus r. So basically what that means is that you can achieve tau is 1 minus r minus epsilon for all epsilon greater than 0.
The list won't be polynomial.
The list will be the list will be polynomial in 1 over epsilon. How large it needs to be, actually things like that are still not fully known, but for that let me make a definition. So when you say this problem, if you want to solve this problem efficiently, it better be the case that the code, even before you think algorithms, the code must have a certain combinatorial sparsity property, because no matter what point you take in a ball of radius tau around it, you should not have too many code words, because if you have too many code words, you're not going to output it quickly. So that prompts us a definition. Let's say C is supposed to be tau comma L list decodable, and this is the other parameter, list size. If for all y in sigma to the n, the intersection, let me just say it this way, the number of code words in C such that delta y comma C is at most tau n is at most n. So there are not more than L code words. Okay. And really what you would like is, you would like for tau to be large. It cannot be larger than 1 minus r. You can prove that. If tau becomes larger than 1 minus r, the fact, what I meant by saying correction is hopeless would simply manifest itself by the fact that this L would be exponential or super polynomial. So that's what it means, that you cannot go beyond that. But it turns out you can really approach tau is 1 minus r. So here is a theorem from 80s. It's an easy theorem. So there exists, let me write it fully, there exists 1 minus r minus epsilon, 1 over epsilon list decodable code. Let me abbreviate list decodable by LD, code over alphabet sigma, which is at most exponential in order 1 over epsilon. Okay, I'm skipping some orders for simplicity.
There's no n in
there's no n anywhere actually. So, and when I say this, it means a family. What it means is, give me an epsilon and an r. I can find a family of codes over a fixed alphabet size, which is exponential in 1 over epsilon, which allows me to correct this fraction of errors with an ambiguity 1 over epsilon. Okay. And when I say there exists a code, typically we always mean a family of codes. So for all large enough lengths or infinitely many lengths, we will have a code of this form. Sorry? Oh, this is this would be Ziablo-Pinsker, I think. But But the proof is really quite, the proof is very simple probabilistic method. Pick a random code, that's it. Zablo-Pinsker also had some results for linear codes and stuff, so I'm not going to get into that distinction. But to prove this is very easy. So you just simply take,
So
these are not linear codes. Yeah. In fact, whether for linear you could get these things, etc., only slowly being resolved even today. So still. But this basically, you pick a random code of rate r, you can prove that and take a union bound over all balls of this radius, and then there's really not much. It's just some calculation.
So is this large alphabet essential?
Yeah, that's a good question. So this is basically tight. So you cannot beat, you cannot be better than exponential 1 over epsilon if you want to be within epsilon of this. This is what I call list decoding capacity, this 1 minus r. So this is inherent. Random codes achieve this. The best codes can't do better than this. This 1 over epsilon is not known to be inherent. So the lower bound is like log 1 over epsilon, and the upper bound is 1 over epsilon. We don't know the truth. Okay, so it's still some.
I'm a bit confused, sorry. So L you would like to be 1, right?
L you would like to be 1, but the moment tau exceeds 1 minus r over 2, you cannot achieve L equals 1.
So what if I put epsilon equal to 1?
Oh, but then this will not say anything interesting, right? So yeah, and I guess I don't think I'm adding a constant factor, but yeah. So. But typically, it's likely that there is an order 1 over epsilon and order 1 over epsilon. Yeah, you would like L to be 1, but you cannot do this. And in fact, it's needed. If you want to approach 1 minus r, the list has to grow. Whether it has to grow as 1 over epsilon, we do not know. But that seems like a tricky question. Actually, Srivatsan, who was an intern here till I guess last week or so, worked on that. And we have some results of that. Okay, so that's all. So, okay, this is great, but this is in some sense a useless result because it just says pick a random code that's going to have this property. So, this raises basically challenges similar to other challenges in combinatorics. Whenever a probabilistic method tells you some object exists, you would like to construct it explicitly. But since codes are also used algorithmically, and you also want to solve list decoding efficiently. Because note that this is simply a combinatorial property. It says that there aren't too many code words, but you would need somehow, not only would you like to construct such a code, but you would also like that code to have some nice structure which you can exploit to find all the close by code words efficiently in polynomial time. So solve this decoding in poly time. So these are the challenges, and so these have been, so what the inspiration for what I'm going to talk about today is that these challenges have been to some extent nicely met in the last few years. Let's say that more or less met. There's still always open questions. So a few years back, Atri Rudra and I gave a construction of a variant of Reed-Solomon codes called folded Reed-Solomon codes, which basically achieved. So we showed something like this: explicit codes. So this was with so this was good in the sense that it for the first time nailed down the correct trade-off between tau and r. So you could actually go all the way up to this. And I should actually say that this 1 minus r over 2, there are classical algorithms. The old algorithms for decoding Reed-Solomon codes allow you to achieve 1 minus r over 2 efficiently. But and I'll state some other results shortly, but we were able to achieve this trade-off. But the problem was, and it was explicit, and it was efficiently poly time, or it was n to the order 1 over epsilon time decodable. So for a first cut, it was good because it nailed down tau versus r quite nicely. And the drawbacks are sort of evident from the bounds here is that the list size, instead of being poly 1 over epsilon, it's n to the 1 over epsilon. It's not even a constant. And the running time is also not great. It's n to the 1 over epsilon. It's polynomial only for a fixed epsilon. Okay, so you would like to maybe make this a fixed polynomial and this something 1 over epsilon. Okay, so the impetus for this talk is the linear algebraic method for decoding. So last 1 to 2 years, this linear algebraic method has improved this in a couple of ways. So there are two choices you can have. So you can have a fully explicit code. So don't get too caught up in parameters. I'm just writing this for context, and then the technical part should be independent of all this. The explicit. Okay, so this basically takes these folder Reed-Solomon codes and combines them with these subspace-evasive sets of the sort constructed by Twir and Lovett. Or you can also pick those objects randomly, and then you get something nice. You get really everything nice, but so you actually nail down the list size also correctly, and both of these are efficiently list decodable. But this is Monte Carlo. Okay, so and I hope to at least define these subspace-evasive sets by the end of the talk. So there's a certain algebraic object you need, and the explicit constructions don't quite match up with the random ones, and that's the discrepancy in these. Okay. Oh, the alphabet size. So in these things is n to the 1 over epsilon square, and those are retained here. So we can improve the alphabet size here to also exponential in 1 over epsilon square. So this latter result will get everything more or less right, except for the Monte Carlo part. Okay, but for simplicity, I'll keep the alphabet size kind of floating in the talk. So in the talk it will be large, but basically by replacing these Reed-Solomon polynomials by more general algebraic function fields, you can make those constant as well. Okay, so that's also recent work with chopping, but that's not the angle I'm going to focus on today. Okay, so what do I want to talk about today is I won't be able to give. So I want to talk about Reed-Solomon codes and a way to list decode them, which enables us to get some result like this. Okay, so what I'll talk about today is a new approach to this. Ooh. Goal of the talk or the goal of the work? Where are we going? Yeah, good. Yeah, I think I left you a little dangling there. Yeah. So this is all context. Okay, so this was obtained using certain things called folder Reed-Solomon codes, and what I want to focus on is an alternate approach using only Reed-Solomon codes to get this result. This second result. Okay, but I won't be able to.
But it's decodable. Unlike
yeah. So yeah. Yeah, so what I mean by Monte Carlo is that, okay, I should maybe make this clear. It will be a randomized construction which will succeed with high probability. You cannot certify it will work, but it will succeed with high probability, and algorithms will be efficient. You can store this code compactly, and you can do error correction on it efficiently.
So what does succeed mean?
Succeed means it will have this list decoding property,
okay.
This sparsity property, and your associated algorithm will always correct every error pattern of that weight.
So when I'm correct, I can do everything.
Yeah. Yeah, and the correctness will be very high. So in the absence of explicit construction, this is a very reasonable compromise, because it will be nice if you could certify these objects, but other than that, it functionally is as good as explicit in some sense, because you will sample a code, it's going to be good with overwhelming probability, and then you can go ahead and use it. Okay, so there are other coding problems for which we would love to have such results, and we don't.
So you said the old theorem, the random codes have. Of course, they can't be decoded. Right?
They can't be decoded. They can't even be stored compactly.
If I pick a random linear code, is it not true that?
So we don't. So the exact trade-offs are still a bit of a mystery. So we are still working those out. But yeah, they're generally good. Random linear codes would be good. So the storing part is not a problem, but decoding is a problem.
We don't know how to decode random linear codes.
Yeah, that's the problem. Yeah. These are in some sense structured ensembles of codes which allow you to decode. Okay.
Sorry, I'm still confused.
Mm-hmm.
So you're saying with high probability you'll get a code
Yeah.
that you can decode.
Yes.
So why is that not an explicit code then?
Because you can't certify.
I cannot certify it.
You can't certify. How do I know that the code that I've picked is satisfying the properties that I'm claiming that it is, right?
That's why I call it Monte Carlo. But you're right in some sense. Functionally, it's as good as. It'll be nice to have a bulletproof explicit construction, but this is functionally more or less sufficient. Yeah. Okay, and to answer Nishit's question, I want to give some glimpse of this, but I won't really be able to get to these parameters and so on. Really, I'll just show the main algebraic idea, and that should be a self-contained story. And oh boy, now comes the challenge. Okay, so now I'll talk about Reed-Solomon codes, which I'm sure all of you have heard of. So I'll introduce Reed-Solomon codes, and so basically I'll show that a certain kind of Reed-Solomon codes admits for some nice decoding, and that's somehow the basis for this new approach to get that result. So there are a couple of ways to get that result, and I'm going to tell you one way which is nice because it just uses Reed-Solomon codes. So Reed-Solomon code, the message is going to be some polynomial f over some finite field, let's say fq, which is f0 plus f1x. So I want the message to have k symbols, so I'll make it a degree k minus 1 polynomial. And the way you encode f is basically by taking its values at n distinct points. Okay, so this requires a large field. So pretty much all the constructions I'll talk about require large alphabets. Okay, but by replacing Reed-Solomon by algebraic geometry codes, you can bring that down to close to this thing, though I won't mention that here. Okay, but now actually let me make this field a blanket f. No, so just not say q, because I'm going to use q for something else. So now what I'm going to do is a variant of Reed-Solomon codes, which has, so here the point is these alpha i's can be any elements of the field. You can pick them to be anything, and it makes sense actually to pick all the elements of the field, so that then you're using the field to the fullest. But those things seem hard to decode. And one thing I should mention about these Reed-Solomon codes is that for this tau equals 1 minus, so the rate of this code is of course k over n, k messages, k symbols go to n symbols. So for tau is 1 minus r over 2, so you can do efficient unique decoding, has been known for 50 years. And there are many different algorithms used in practice and so on, but the first algorithm was from 1960. So it's a long time back, even before P was defined. Right? So it's one of the early non-trivial polynomial time algorithms. And for list decoding, the best thing which we know is work with Madhu, where we get 1 minus square root r, and that if you plot here will be some curve like this. So it does beat 1 minus r over 2 always, the traditional bound, but it falls short of going all the way. So
multiplicity codes can essentially bridge that gap, right?
not in this setting. Oh, you mean the univariate multiplicity codes? Yes, they can bridge the gap also.
So this power root can be replaced by 1
Yeah,
minus
yeah.
epsilon.
The folded can and the multiplicity can. And now I will talk about a particular Reed-Solomon itself, which can go beyond this.
So then again I'm confused. So what's the specific advantage?
Oh, what? No, it's just alternate constructions, and I guess some of this landscape is getting simplified over the years, right? So I want to talk about a particularly simple code which allows you to go beyond 1 minus r over 2. Right? So, and this is for general Reed-Solomon codes, this remains the best known. I'll show a specific Reed-Solomon code where in some sense we are able to go beyond this. Not strictly because I'll need all the subspace-evasive sets, there's the Monte Carlo and all those things, but it at least shows that whether we can beat this is it's not clear what the answer is. Okay, so this is the best known for general RS codes, for Reed-Solomon codes. Okay, so now what I'm going to do is I'm going to play with the fact that, so these results really don't care what your evaluation points are. You can pick any n elements of their field. Okay, and that's a nice aspect of those results. But now I'm going to say that, well, I'm going to pick a specific collection of points. And in fact, I'm going to take my field f to be an extension field, fq to the m. And I will pick my evaluation points to just be points in the subfield. So in some sense, I'm being wasteful because I have q to the m points, but I'm only going to evaluate at q points. So already these codes are worse in one sense. Their alphabet size is kind of bad. As a function of n, they are not n. Here the alphabet size is at least n. Now it's going to be at least n to the m. Okay. So now I'll do the same thing. So f will now be a polynomial over the extension field. Everything happens over this big field. It's just that the evaluation points are going to be in my subfield. And that will now be in f of alpha 1 to f of alpha n. So n has got to be less than q, alpha I are in the subfield. Okay, that's my Reed-Solomon code. It's also a Reed-Solomon code, but now for this code, I'll try to give an algorithm. And this algorithm will really sound, it's really very similar to this Welch-Berlekamp algorithm, which we have seen before. So it's actually going to be very easy to to get up to some point, at which point we will need subspace evasive sets, and I'll also run out of time. So that's the agenda. So, okay, so hopefully it's clear what I'm doing. I'm trying to give an algorithm to decode this code, and we will see how that algorithm goes. So you send f of alpha 1 to f of alpha n. This is your code word, and it gets distorted to some string y1 through yn. This is our model, and our assumption is that at most tau less than or equal to tau n errors happen. And what we would like to do is we get this, we don't know what f is, so we would like to go back. From this we would like to find f, or find a list of possible f. Okay, that's our problem. Okay, how are we going to solve this? So it's going to be for those who have seen similar algorithms, it's going to follow the same framework. There will be a step where you interpolate a nice algebraic condition, and then that condition will give you some handle on what the f can be, and you try to find what the f is. Okay, so everything should be really quite simple. So the algorithm will use two parameters. So this is now the algorithm. So I'm going to talk about the algorithm. So you take two parameters. So one of them will be an integer parameter, which is between 1 and m. And when you take this parameter s to be 1, you're going to exactly get the Welch-Perlek algorithm. Okay, so it's just, so this s is some sense will be a higher dimensional generalization of that algorithm. And another parameter will be some degree parameter d. Okay, so I'll just call it d. Okay, so let's see how to. Okay, so the first what we are going to have is the following. So here is a lemma. So there exists a polynomial. So instead of giving the algorithm, I'll give a lemma which asserts that a certain kind of polynomial exists, and the algorithm will really find that polynomial. Because I'm sort of developing the algorithm as we go, okay, along with its proof. So there exists a polynomial q in many variables, q, x, y1, y2 to ys. It's going to have x for this, and then it's going to have s extra variables. And it's going to be of a very simple form. It's going to be a linear polynomial in the yi's. Okay, so it's going to have degree exactly 1 in all the yi's. Okay, and you won't even allow y1, y2 terms with degree of is ai at most d. So I'll also pick d. Actually, I'm going to tell you what d is. Okay, roughly think of it as n minus k by s plus 1. Okay, you will see why.
It's analog of error locator polynomial.
Yeah, it's very similar to that. Yeah. So basically, what I'm going to pick degree large enough so that a polynomial of with some degree restrictions satisfying some interpolation conditions will exist. Okay, that's what this lemma is going to assert. So degree of ai is at most d for I equals 1 to s, and the first guy I can allow even slightly bigger degree. It doesn't matter. Such that, and here comes the key point. So this polynomial is supposed to do something about, you're going to be given this received word, and this lemma, what you will do, the algorithm will do is find a polynomial of the form asserted by this lemma. And this is where you bring in the yi's. So alpha I, yi. So this yi is supposed to be the evaluation of f at alpha I. So you pair that up, and you also have some extra things. So yi to the sig q, yi to the q to the s minus 1 is 0 for I equals 1, 2 to n. And I should say there exists a non-zero polynomial. Okay, so all I've said is that there's a polynomial of this form. It has some degree restrictions on x for each term, and its degree in yi's is 1. So it's a very simple form, and it obeys these n linear conditions. And further, it can be found in such q can be found in n cube time, let's say, or n cube field operations to be accurate. And the proof of this is really simple. See, each of these conditions, so finding q is really finding these ai's, okay, which is the same thing as finding their coefficients. And each of these conditions that you vanish at this point, remember the alpha i's and y i's are fixed elements in the field. So those are not variables, those are fixed scalars. So when you substitute this, you're going to get one linear, each of these is going to be a single linear condition on these coefficients. Okay, so you will have a non-zero solution the moment the number of degrees of freedom here, number of variables exceeds the number of conditions. Okay, the proof is basically the number of degrees of freedom in Q is, what is it? Well, for each of these d a1 through as, I have d degree condition d. That means d plus 1 variables, right? Because you can have the 0, x to the 0, x to the 1, all the way to x to the d. So you have d plus 1 choices. So you have d plus 1, and that happens s times. And now this a0 allows you d plus k choices. So you have this. Okay, and I really picked d to be n minus k by s plus 1 just because d times s plus 1 plus this should be more than n. This is more than n for our choice of d. So you have n equations and more than n variables, so you will have a non-zero solution. And finding such a Q is also easy because it's just solving a linear system. Okay, so the algorithm, that will be the first step to find such an algorithm. So I'll go first step. So this is the algorithm. Let me leave it here. So first step, find Q as in lemma. Okay, any such Q will be fine. Okay, so at least one exists and you find it. That's very good. Now what we want to do is we want to say that if you have such a Q, remember my goal is to find what f is. So I'll use this Q to somehow pin down what f is to a small list of possibilities. Okay, that's how the traditional, all the list decoding algorithms, the 1 minus square root r, etc. go that way. Okay, the exact style, exact structure of Q varies from different algorithms, and the details of the second step also varies, but the overall structure is the same. Okay, so 2 is to be filled in. So basically now what I'll prove is the following. So if tau is less than or equal to s over s plus 1 times 1 minus r, remember r is k over n. So if the error fraction, so I want to correct some tau fraction of errors, and I will say that if tau isn't too big, well, how big? It's going to be s over s plus 1 times 1 minus r. Then I'll say something nice happens. Now when s is 1, this is just 1 minus r over 2. So you will revert back to just your age-old Welch-Perlecamp algorithm. But the point is, it gives you the flexibility to increase s. So by picking s larger and larger, you can approach 1 minus r. So you take s to be 1 over epsilon. This would be more than 1 minus r minus epsilon. Okay, so then, so when I say this, what I mean is that you sent f, you received yi, and the number of errors was at most this. So then I want to say that any q you find in this first step will have some nice property. Then q, let me write this down in a, let me write it in a slightly different way. So a0x plus a1x fx plus a2x f sigma x so then some algebraic condition involving f must be satisfied. So here, to make sense of this, I need to define what, so this should be clear, but what is f sigma of x? Well, f sigma of x, if f was f0 plus f1 and so on, this sigma is going to be this Frobenius automorphism of this extension field over the space field. So you'll simply power each of the coefficients by q. So f sigma x will be defined as f0 to the q plus f1 to the qx and so on, fk minus 1 to the q k minus 1. And f sigma square is just iterate. So f sigma square of x is f sigma of x and so on. Okay, so this will have f sigma square will have f0 to the q square plus f1 to the q square x and so on. So all you're really doing is playing games with the coefficients of the polynomial. You're taking the polynomial and powering each of these. So these polynomials are somehow closely related to f. And I'm saying if too many errors did not happen, find me any polynomial q of this form, then my f must satisfy this sort of equation. Okay, and now somehow I have to make use of this equation to find f. Okay, I still have to cross that hurdle. Okay, I'll come to that in a second. But why is this true? Okay, this is really the key. So far, you might have wondered why on earth I picked alpha i's to be in FQ. Okay, and this is in some sense it's simple, but this is the new part, the new algebraic part. Okay, and the proof of this is quite easy. So let me actually make a definition. Let me define phi of x to be q of x, fx, f sigma x, and so on, f sigma to the s minus 1x. It's just notation. So all I'm really claiming is phi x is 0. Right? I want to prove this polynomial is 0 because this q is of this form, so I'm just substituting f for y1, f sigma for y2, and so on. Okay, that's now becomes a polynomial only in x because I've substituted polynomials in x for the remaining yi's. And the goal is to prove phi is 0.
Sorry, so just to recap everything.
Yeah.
So the point about the first lemma was that q with these substitutions of y's.
Yeah.
I mean, where the variables are related in that way is 0 for every I.
Yes, every I.
Now, you are somehow going to use the fact that q has a certain degree, so if it's 0 at a certain number of points, it's
Yeah.
0 everywhere.
Yeah. But not q, but to this polynomial phi. Yeah, yeah,
Okay.
yeah.
To say that
Yeah.
if you have
Yeah.
few errors, then phi or something related to that is going to be 0 at enough spots
Yeah, exactly.
compared to degree so that it's uniform. That's what you
That's a proof. Yeah.
So this is like a standard trick used in identity testing all the time. So
Yeah, and this is
Exactly, because it's usual.
yeah, this is the same as the original Reed-Solomon and so on. Just the structure of this phi, etc., is different. Yeah. But really, it's how you prove a polynomial is 0 is exactly count degrees and roots. So let's do that. So degree of phi, that's easy. Well, these AIs had these degree restrictions. And now what I'm doing is I'm taking each yi and putting in a degree k minus 1 polynomial. So each of these becomes d plus k minus 1 also. And that's why you have this slight imbalance. The first guy doesn't get it. So if you're wondering the thing, that's just... And therefore, because of that, the degree of phi as a polynomial in x is at most d plus k minus 1. Right? That's just by construction. And now, on the other hand, here comes the key point. If f of alpha I is equal to yi, then I claim phi of alpha I is actually 0. And this is exactly similar to old things where the way you use correct points is to somehow manufacture zeros for some polynomial. So if you have enough correct places, you'll be 0 to too many times and some nice algebraic condition will fall. And this is really easy because, well, let's just substitute. What is phi of alpha I? So I want to prove this. Phi of alpha I is q of alpha I, f of alpha I, f sigma of alpha I, and so on. Okay, that's just definition. And now the main point is, let's just look at the first guy. What is f sigma of alpha I? It's basically you take these things and now put alpha I. But so I claim f sigma of alpha I, let me write it here, is also equal to f of alpha I to the q. Okay, and let me prove that in this direction. What is this? This is f0 plus f1 alpha dot fk minus 1 alpha to the k minus 1. Okay, alpha I, right, to the q. Now everything happens over, in the characteristic is divisor of q, so you're raising it to a power of the characteristic, so that's a nice thing, so you will just get this. You can take the power of q's inside. Q to the k minus 1. Okay, and now, okay.
it's not a power of 2, I guess.
Sorry?
It's not a power of 2.
No, I think q can be a power of 2. I don't think anything. There's no such restriction. You're just using the fact that this operation happens in fq to the m, and the power is 2q. Right? So you take it inside, and now comes the key point. Okay, why did I pick alpha I to be in fq? Now I can say alpha I to the q is just alpha I. So at this point, this just becomes f0 to the q plus f1 to the q alpha I plus f1 to the f2 to the q alpha I square, fk to the q alpha I to the k minus 1. And that's, of course, f sigma at alpha. Okay, so that's the small amount of magic here, and that's equal to q. So okay, we are still not done. So because of that, well, this point, because of assumption, is yi. And this point is yi to the q by that. And successively, the other guys are all higher powers. Okay? And this is 0 because that's the way I interpolated q. Okay, and now it's basically just a calculation. So whenever you have an agreement, you get a 0. So we just have to compute how many zeros do we have? So we have at least n minus tau n zeros, and tau is supposed to be at most s over. Now tau is at most, tau n is at, so this is at least n minus s over s plus 1 times n minus k. Right, because tau n is, you just take n inside, it's n minus k. Okay, and this you can check is at least d plus k or something.
So one sort of a side question, you don't need, I mean, you just need the total degree or whatever to be high enough.
Yeah.
So for instance, if I somehow knew, I mean, I don't know why I would know, if I somehow knew y1 is more likely to be erroneous than, I mean, if I, different bits have different likelihood of whatever it being.
Right.
You can adjust your degrees so that you catch them, right? I mean,
so if you knew that, actually the right thing would be to not adjust the degrees per se, but adjust the interpolation condition. For example, if you knew that y1 is, if you knew something is likely to be correct, then you should give it more importance and maybe make sure that at this point you don't get only 1 0, but you get higher order multiplicities. And that's actually the key to this 1 minus square root r. Okay, that of course does treat all points to be equal, but in some sense the practical use of this 1 minus square root r result was precisely this point, that not all points are created equal, and somehow the technique we used here to give different points multiplicities was useful to encode that information.
Well, I think if you have stochastic channels, I think that's probably what you're referring to.
No, this is like the same.
Yeah.
No, but I mean, if you have information, then it's not a good thing. If you know that some bits are more likely to.
Right. Yeah.
So stochastic channels are very easy.
Right, but the way you say people use this result to get soft decoding was to somehow encode that with higher multiplicities. But turns out for this style of doing things, we don't quite have that much flexibility because we are really tying our hands to this style of polynomial. So what we could do in this kind of result is that, okay, you want to pass through each point twice with multiplicity, we could simply just square this polynomial. Right, your degree would double, and the point
You're
was
saying keeping a not a
Yeah.
of different degree doesn't.
it seems to be a losing game, the parameters. Yeah. It's not immediately clear, but that's sadly the way the parameters seem to work out. And that's it. So you just and this is what allows you to correct these many errors. Okay, d was like n minus k by s plus 1. So if you add these two, you're going to get roughly this. Okay, that's good. So okay, I have 10 more minutes, I guess. So we have come some way in the sense that I've at least shown you that you can correct this many errors and get some non-trivial handle on f. Okay, and I'll actually show that this is a non-trivial handle next, but so far you at least see that f cannot just be any old polynomial, it better obey this condition. Okay, and now what I want to do in the remaining time is just maybe inspect this equation a little bit and show you that, okay, it does tell you something non-trivial about f.
You have to argue the number of x.
Yes, small. Yeah, we won't be able to argue that, and that's where the subspace-evasive is. Okay, the journey is actually just begun, but at least the point is, the algebra is clean and simple enough that I can fully explain it. And hopefully I'll also give you a taste of why these subspace-evasive type things show up. Okay, so here is another, let's see. Okay, let me not write down a lemma, but rather let me just focus on this equation and see what it tells us. So let's actually make some notation. So let's say ai of x is ai0 plus ai1 x plus ai2 x square and so on. Okay, just remember I'm told what the ai's are by the first step. Okay, so now the second step of the algorithm would be solve this equation star for f somehow. Okay, that's what I have to tell you. So this is my handle on f, and I need to figure out what f is. So I know what the ai's are. I don't know what f is. So I need to know the coefficients. So f0, f1, f2, and all that. Fk minus 1. I need to find this. And how am I going to do this? Well, it's an equation. It says a certain polynomial is exactly 0. So that means the constant term is 0, the x term is 0, and so on. So let's just do that. Let's say write what the constant term is. So just to give you, to cut a long story short, what I'm going to show you is, and that's the term linear algebraic, is that this condition is actually a linear system on the coefficients of f. And as such, the solution will be an affine space which has non-trivially small dimension. It will still be large dimension, so we won't quite be done, but it will be small enough that we can play the subspace evasive game and go on with it. Okay, so that's what I want to show. So let's write down the constant term. Well, you get a constant term only from the constant term, so that's easy. So you get A00 plus A10 F0 plus A20 F0 to the q, because remember here it's F sigma. The constant term of that is F0 to the q, and so on and so forth. AS0 F0 to the q to the s minus 1. This has to be 0 because it's the constant term of this polynomial. Okay, so this can be written as A00 plus some polynomial, and b, let me call it b0 of f0 is 0. Right, this is a polynomial. Now, as such, this is good because it says it already pins down f0 to not too many possibilities, right? Because this b0 has degree q to the s minus 1. So the number of solutions to this can be at most q to the s minus 1, because it's a degree q to the s minus 1 equation. So it's already something non-trivial, because remember the fi's live in, or let me say fj's live in the big field fq to the m. But now I'm saying f0 does not have all that flexibility. It only has to have q to the s minus 1 possibilities. So that's some progress. But it's more than that, because actually this is actually an fq linear condition. On f0. Okay, there are a couple of ways to see. So the point is, raising to these things is actually a linear operator. Because f0 lies in the extension field, you can write it as a vector of length m1 over the base field fq. Okay, and then you can prove that this gives you a linear transformation, and so solutions will be in an affine space. Not trace operator. Another way to say it is that this b0 is what is called as a linearized polynomial. Right. So the map x goes to b0x is an fq linear map on the extension field. Right. And therefore the solutions to this will be in affine space. Okay, this is standard fact about linearized polynomials, that suppose I just took a linearized polynomial and said it's give me all points where it's 0, that will be a linear subspace. And if I say all the points where it's equal to something, it's an affine subspace.
Trace is just the sum.
Or trace would be you go all the way up to q to the m minus 1. This is some sort of, you truncate the trace somewhere. So, are precisely these, yeah. So this gives you a linearized polynomial of linearized degree s minus 1. So so again, even if this wasn't clear, just trust me, standard fact is that therefore f0 belongs to dimension less than or equal to s minus 1 affine space subspace of fq to the m. Remember, this was an m dimensional subspace of over fq, but now because of all the things I have done, I can tell you that f0 cannot be anywhere. It has to be in a specific s minus 1 dimensional subspace of this over fq. Okay, if affine fq subspace. Linearity is always over the base. Okay, that already seems like non-trivial information, and you can go further. So I don't want to bore you with calculations, but you can maybe I'll write down one more what you get. Actually, in general, this is what you will get. So the general equation pattern will be the jth point will be this: b j f0 plus b j minus 1. So these will be some fixed polynomials plus b0 fj is 0. So this is by saying the coefficient of x to the j in that polynomial is 0, you will get an equation of this form. And so the point therefore being that if once you fix for each choice of f0, f1 to fj minus 1, this is just going to be some fixed number, fixed element in fq to the m, and you're basically going to say that fj must be in a particular affine space of low dimension. Okay, that's going to be the structure. And immediately this also shows you that the number of solutions to this cannot be too large. Why? Because f0 has at most q to the s minus 1 choices. For each of those choices, f1 will have at most q to the s minus 1 choices. Okay, so therefore just inductively the number of solutions to that, so lemma, and what I did is essentially prove that lemma without kind of And even getting this is exactly similar. Okay, just calculating. The number of solutions to star being that functional equation, is at most q to the s minus 1 times k, the exponent. Okay. So two things. One, this is not very good, right? Because it's q to the s minus 1 to the k, and k is growing for us. The rate is k over n, so this is like q to the s minus 1 to the r times n. So n is in the exponent. That's not what we want. So this is not polynomial. That's bad. But also note that this is something non-trivial, right? Okay, it's already clear from this what I said, but just in terms of comparison, the total number of possible f's is q to the m times k, because each coefficient is q to the m possibilities. And now I pinned it down to some non-trivial subset, which is A, much smaller, but also B has some nice structure. Okay, it's basically some affine subspace. So it's actually also, the same lemma also shows that the solutions not only have at most this, in fact let me write it lemma differently. The solutions to star lie in a dimension less than or equal to s minus 1 k affine subspace of f q to the n. Oh boy. Okay, and the second part just follows from that, because it's a low dimensional subspace. Okay, and the proof of that is just this fact. This calculation shows this. So it's a non-trivial information in the sense that you have this big set of polynomials, possibilities, and now I have non-trivially pinned it down to a low dimensional subspace. But it's not small enough for me to be done. It's still too big. Okay, so I'm basically out of time, but this is kind of what I wanted to end with, which is the second part of the talk. At least I want to say why this subspace evasive sets come. Okay, so at least I'll give you the high level idea, though the exact execution in this particular case is actually more complicated, because you cannot quite have good enough subspace evasive sets of this form. Okay, so what is a subspace evasive set? But before that, let me give you some view. So you have this fq to the, so let me just make f to be the extension field itself, right? So you have a k dimensional subspace. Originally you're saying your messages can be anything in this thing. But now what I've done at the end of this whole decoding process is I've said that, hey, here is a smaller subspace of this space, and my f should lie inside this. Okay, that subspace is too big. But now is a simple idea is that, okay, natural thing to try maybe is not allow all f's as messages, but only those in some crazy subset, which is still quite large, but intersects every low dimensional subspace in few points. And that's my subspace evasive set. So let me make a definition. A subset of f to the k is, let me call it R comma L subspace evasive if for all subspace H of dimension, let me say affine subspace of dimension at most R, H intersection S is not too big. Suppose I had in my hand, suppose I did not allow arbitrary f's as messages, but only those f's which intersected every low dimensional subspace in few points. Then there is some hope that I'll be in business, because at this point I know that this algorithm has pinned down my f's to a small subspace, and I know in that subspace only a small number will be legal messages. We all know this. I mean, the sender and receiver agree on a code, which is this crazy set. Okay, this raises some challenges. First of all, do these things exist? Okay, maybe if you have to intersect every low dimensional subspace in few points, then you cannot have too many points. Right? But fortunately, it turns out random objects are amazing. So just a simple probabilistic method. So this is the probabilistic method again. Says that suppose, let me just try to write this. Suppose R is not too big. Okay, so clearly you cannot. If I make R equal to k and you want to have few points in the whole subspace, you cannot be too big. So I need some upper bound on R. Let's say R is at most say epsilon times k. Then there exists an R comma R over epsilon subspace evasive set of size f to the 1 minus epsilon times k. So basically this says that you can pick a subset which is, instead of f to the k, it's f to the 0.99 times k, quite large, and yet you won't intersect fairly large subspaces in more than r over epsilon points.
This is random subset.
This is a random subset.
Just some VC dimensional number of subspaces.
No, it's you can do
Just count.
even just you don't even need VC dimension for this. You can just count all subspaces of that dimension to a union bound. Okay, and this argument doesn't even need full independence; it only requires r over epsilon wise independence. So you can actually sample such a set in a pseudo random way. Okay, so by just limited wise independence. Okay, that's good, but the challenges so in some sense morally we are done, because what we want to now do is take our Reed-Solomon code, instead of arbitrary polynomials, only take those guys in this subspace evasive set. Okay, and such subspace evasive sets, they are random, you can also construct them pseudo random by using some limited wise independence things. But the trouble is, fine, so in some sense that will already ensure this combinatorial list decoding property for you. But if you want to go ahead and find this intersection, you are in trouble, because this is some pseudo random crazy set, and I give you a subspace and ask you what are all the points of your crazy set in this subspace. Well, the naive thing to do would be to just look at everybody in that subspace and see if it's what it means to say that you have the set is that you have some membership oracle for the set. So you could take every point in the subspace and say, are you in this set or not, and keep going, but that's going to take too much time because your subspace is too large. Okay. So that's the problem. So I won't get into that. But the way you finesse that issue is that this subspace is not an arbitrary subspace, but it has some nice periodic structure. The first f0 itself is in a low dimensional part. And then for each fixing of f0, the next f1 is in a low dimensional part. And each of those parts aren't too big. And so you use that in some inductive way to carefully construct such a set, which also allows you to compute this intersection efficiently. Okay, and that's the whole point. And just to conclude, how you get the 1 minus r minus epsilon is really by taking s to be 1 over epsilon. And then you can pick your m to be a little bit bigger than that, like s over epsilon, and then you are able to, using these kinds of randomized constructions, pin down the list to 1 over epsilon possibilities.
Okay. You have to encode your message into the evasive set.
Exactly. So you cannot simply pick a random set, because you need to encode the message into the evasive set. That also you can do by this pseudo random construction. So basically the subspace evasive set will be parameterized by some random polynomials, and to encode a point will simply be evaluate this random polynomials at some specific places, and that will give you the image. Yeah, there are a lot of technical details in making this work, but the high level idea of the fact that the algebraic list decoder pins down the messages to some structured subspace, and then you use the subspace evasive set to winnow the candidates to the actual ones which belong to your code. Okay, those are the two high level pieces. And you execute them carefully, you get the kind of results.
The Monte Carlo part is just in the subspace.
Monte Carlo part is in the subspace evasive set. So there is an explicit construction due to Dwyer and Lovett, who say that you can get subspace evasive sets where the list size instead of r over epsilon is exponential in R. It's something like r to the r. And that's kind of good enough for the original folded Reed-Solomon codes, but here it's bad because R itself is linear, right? So we do not have good enough explicit constructions. So if you want a beautiful open problem, really constructing explicit subspace evasive sets where you get something like this, where let's even fix epsilon to be half, right? So can you get f to the k over 2 points, which intersects every r dimensional subspace in poly r points. That will be very nice. The current approach only gets exponential in R. So I'll stop there, but we can continue discussions if there are questions.
So Venkat will be here all day today, or until sometime in the evening, and tomorrow morning, right?
Yeah.
So feel free to chat with him about everything.
Okay.
So I'm just trying to see if there's a simpler way to see that this is a linear constraint.
Oh, yeah, there is. Yeah.
If I forget about the a naught of x, which is like the
Yeah, yeah, yeah.
Then
That just makes linear to affine. That's all. Yeah,
so
yeah.
then for any f and any g that satisfies this,
Yeah,
f plus g
that's-
satisfies. That's it.
That's it. That's it. Yeah, exactly. So this is clearly a linear FQ linear system in the coefficients of
So the only restriction on the alpha is that they have to lie in FQ.
FQ. Yeah.
But in FQ I can choose any.
Yeah, you can choose anything. And there doesn't seem to be an advantage to delineate further within FQ. So you can basically here pick the whole of FQ if you want. Yeah.
But the encoding itself has a step which puts it in the subspace. You cannot choose any, just the normal F.
No, the encoding into subspace evasive set will say that the f's are not arbitrary, but together f0, f1 to fk minus 1 must belong to this subset which you stipulate.
But my message could belong, initial message could belong anywhere in.
Right. The initial message will belong to any, initial message will be in f to the 1 minus epsilon times k, and from that you will map it to fq to the k, and that image of that map will be this subset. That was Ravi's question, which is you also need this subset to be the image of an efficiently computable map, so that you can encode into that subset or index into that subset. If you say, give me the 10th element of the subset, you should be able to do that quickly. Okay. Should I erase this? Or
No, somebody,
somebody will throw acid on it. And
right.